So in this video, we're going to start talking about techniques and tests that are going to help us identify whether a certain series converges or diverges, other than like doing the partial sums, calculating them, and finding like a general formula, then taking the limit. So that's a lot of steps. So there are some tests that we're going to learn that's going to make things a lot easier. So the tests that we're going to learn in this section is the divergence test, the integral, and p-series test. So let's start with the divergence test. This one is pretty easy. If you have an infinite sum, if you take the limit of your an, if this limit is anything other than 0, so if it's any constant that's not 0, or if your limit does not exist, this means that your series is divergent directly. If you have a limit other than 0, then your series diverges. That's it. So that's why this test is the simplest test to apply, because you just take the limit for what's inside of your infinite series. If it's not 0, this means that your series diverges directly. Now, if the limit is equal to 0, we can't say anything about the divergence or convergence of the series. We have to use other tests to see whether our series diverges or converges. So if you evaluate the limit and you get a 0, you need to use other tests to identify whether your series converges or diverges. So let's start with this series. If I have this infinite series of cosine 1 over n, if I want to apply the divergence test, let's take the limit. The limit of cosine 1 over n is going to be equal to 1. Because cosine has the range of -1 and 1, and if it's going to infinity, it can't go above 1. So here, the limit is equal to 1, which means it is not equal to 0. So directly by the divergence test, the series diverges. That's it. Now, the integral test compares an infinite series to an improper integral. So the condition for this test to work is I need to have a sequence or a series with positive terms only. So if this series has positive terms and there's a continuous function that's decreasing, where f of n is equal to a of n, for any number bigger than a certain value n capital, then this means I can compare my infinite series to this improper integral. So we know how to evaluate improper integral. You evaluate the improper integral. If it converges, then the infinite series converges. If it diverges, then the infinite series diverges. So what we have to pay attention here is, although that the convergence of the integral, the improper integral, determines that the series is convergent, that does not mean that the integral and series converge to the same value. So we have to be careful here. Like the answer that you get for the improper integral, even though it means that your series converges, but that does not mean that the series is equal to that value. So let's try this series. We want to determine whether this series converges or diverges using the integral test. So using the integral test, I'm going to compare this infinite series to this improper integral. So let's take your n capital to be 1. Doesn't matter, as long as your function is continuous at it. So to evaluate an improper integral, I'm going to take the limit, right? So we take the limit as t goes to infinity for this. Now if you use a u substitution, you're going to get ln of 3x squared plus 1 once you plug in upper minus lower bounds. So here, once you plug in infinity, ln of infinity is just infinity, so the improper integral diverges. So since the improper integral that we compared the series to diverges, using the integral test, my series diverges too. So that's it. Now, the last type of test that we're going to talk about today is the p-series. So a p-series has this formula. The summation of 1 over n to the p, where p is any real number. We call this a p-series. So this p-series converges if p is bigger than 1. And it diverges if p is less than or equal to 1. As simple as that. So if we have this series, for example, my p is 5 over 4. 5 over 4 is bigger than 1, so using the p-series test, my series converges. That's it. Similarly here, if I have 2 over 5, 2 over 5 is less than 1. Since it's less than 1, using the p-series test, this series diverges. So this is why the harmonic series diverges, because 1 over n has p equals to 1, and using this rule, the summation of 1 over n, or the infinite series of 1 over n, diverges. So all of these tests have long proofs in the book. If you're interested, you can read them through. If you have any questions about these proofs, just email me and we can talk about it. But for now, you can do these problems for extra practice. And if you go to Lumen Homework 4, you can do these problems too. And good luck with everything.